So in chapter 2, we're going to deal with the types of equations that are called functions. They're very important ones, and they're things that we're going to see throughout the rest of the semester. Really, the notation and the things that we do here are going to be we're going to use them very often. Okay, in different contexts, different types of functions. So we're going to talk about all the different details in a function. So the first thing, I think I want to do that. Okay, just a relation. So we'll start off with, this section has a lot of definitions in it, so that's kind of where I'm starting with. The first thing is called a relation. A relation is any relationship between two numbers or two sets of numbers or two variables. Okay, so what we generally do is we call that any set of ordered pairs. Okay, a relation is any set of ordered pairs. Essentially, it's a relationship between two variables. Okay, so now we tend to use x and y for almost all of the functions that we're going to deal with, but you can use any variables that you want. Okay. The ordered pairs that we're referring to are like points, like x, y coordinates. So you guys have probably seen these before. An x, y coordinate is an ordered pair, and so if you have a set of these, a whole bunch of them basically, that represents a relation. Now sometimes these ordered pairs are listed off in this form, but you can have other ways to represent ordered pairs, like graphs, right? The Graphable Line is a list of an infinite number of ordered pairs. You just don't see all of them listed out. You can have them in table form. So like you have an XY table with a bunch of numbers in it, and so forth. So relations can take on any of those forms, but essentially it boils down to a list of numbers that are paired up. Okay, and the order is important. You can have one variable as the first entry and the other variable is the second entry, and it always has to stay that way. So for instance, the point 2, 5 is different from the point 5, 2, right? The order is important. That's why they're called an ordered pair, because if you change the order, then you change the location of that point. So it's a different point. So order is important, and it has to be a pair of things. Okay, so that's the first thing. All of the numbers that can possibly be in the first coordinate are called the domain. You take that set of numbers. So I'll use a different marker here. My black's running out at me. So the domain is the set of values for the, we'll call it the independent variable. The independent variable is the first one. It's the x value. Okay. So we'll call that the x value. It's an independent because usually in equations or in functions, that's the one that you choose and plug into it. The y value is calculated based upon the x value, and so we call that the dependent variable because it depends upon what you choose for the x. Okay, so one's independent, the other one is dependent upon it. The range is the set of values for the dependent variable. Or the y value. Okay, the y values are the dependent variables. Okay. Well, it's so weird. Sometimes I get a little thrown off. When I'm standing here, that looks like it's written straight across, but when I look at the screen, it's definitely on a slant going that way. Weird, that just throws me off. I don't know why. It just occurred to me. Okay, so those are the domains and the ranges. So let me give you a concrete example here of a relation. So you can have, like I said, you could set up an XY table and just list out all of the ordered pairs in that table. So something like, 0, 5, and -2, 17, 6, 31, and 5, 8, stuff like that, right? So let's say these are my 4 ordered pairs, and maybe that's the whole list of ordered pairs for my relation. Okay, so the relation itself is a set of ordered pairs. If this represents the relation, then the actual relation, if I wanted to write it out as a set, is the set containing 0, 5, -2, 17, 6, 31, and 5, 8. Right, so that's a set of ordered pairs. Again, I could write this set in graphical form, or I could just plot the graph of those points. I don't know where they're going to be. I'm not going to go through that, but you have points somewhere. And so you can represent graphs with a set, with a table. I'm sorry, you can represent relations with a set, with a table, with a graph. And sometimes you can even write it out something like y is the product of 5 and x, or something like that. And so you could write it out verbally, or in an English sentence, and that would be a sufficient representation. So there's lots of different ways to represent a function. Okay, so what I wanted to mention then is that the x is the independent variable, the y is the dependent, and the x values, all the values on the left side of this table, represent the domain. All the values on the right side represent the range. And so the domain is going to be 0, -2, 6, and 5. Okay, so it's the set of all the values for the independent variable. The range is going to be 5, 17, 31, and 8. And so it's the set of all values for the dependent variable. Computer fell asleep. Okay. So there's our domain and range in this particular example. What else do I have here? I should probably define what a function is. Oh, actually, I'll give you another example using equation. So another way to represent relations and functions is with an equation. Let me write one of those up here. Stick with kind of an easier one. Something like y equals 5x minus 7. Okay, that's an equation that represents a relation. So there's values that you would plug in for x, and you would get out values for y. Now, if you think about this, I could put them in a table format. The only problem with the table is I'm not going to be able to see all of the ordered pairs, because there's an infinite number of things I can plug in here, right? And so I can't list them all off. It'd be impossible. Maybe I can list a few off and get an idea. So like if I wanted to plug in a 0 and a 1 and a 2 and a 3 for the x value, then I just calculate what the output is. So if I go 0 times 5, right, plug in a 0. So y would be 5 times 0 minus 7, which is 0 minus 7 is negative 7. That's going to be your y value. If I plugged in a 1, I get 5 times 1 minus 7, which is 5 minus 7, which is negative 2. That would be the y value, okay, corresponding to 1. And then 5 times 2 minus 7, 10 minus 7 is 3. And if I plug in the 3, I won't write this one out, but 5 times 3 is 15, minus 7 is 8. And so you can kind of see, you can get a feel for what's going on there. On the left side, as you increase by 1, the right side increases by 5. Kind of interesting. And of course, these keep going, but there's numbers in between there. There's numbers, you know, negative numbers. There's tons of things that we could plug in and make that work out. And so the domain and range are a little bit harder to figure out because I can't just list out the numbers like I could in the last example. Instead, for the domain, I want to think about all the possible numbers that I could plug into this thing. Well, every number can be plugged in, right? There's not a limit to what I can put in for x. No matter what I plug in, I can always multiply it by 5, and I can always subtract 7. There's no issues there. So the domain is what we call all real numbers. And you can write it out as all real numbers, or you could write it as an interval, because all real numbers represents a whole number line. And so when we work with intervals, remember we go with the left interval, the right interval, it's negative infinity to infinity. So think of it as the interval negative infinity to infinity. Okay. That means every number between negative infinity and infinity is in the interval, or is in the domain. There is also a set form or a set notation for all real numbers. Sometimes you'll see this, it's like a capital bold R. We can use that symbol for all real numbers as well. So personally, to me, it doesn't matter which of these three you use. My math lab has its preferences. I can't remember which one. I think it prefers the interval form, but you might just, you know, check it and make sure that you're reading through the instructions. I'm pretty sure it's going to want the interval form when you need to use that. Now, in a similar way, the range is all of the outputs, or all of the things that you get out from the or get out for y when you plug in the x. And what's interesting about this is that no matter what value we get out, there's always something that you could plug in to get it. And so the range of this thing ends up being all real numbers as well. It's not real easy to like, you can't calculate that, or you just kind of have to think about what's going on here. And I'll give you some tricks to trying to figure out domains and ranges later. So the range in this case is also going to be all real numbers. One of those tricks is to plot a graph of the equation. And so this ends up being a linear equation. We'll talk more about linear equations and how to graph them, the slope-intercept form and things like that later. I think it may even be later in this chapter. No. Yes. No. I don't know. Yeah, linear function. So in like section 2.4 and stuff. But for right now, just know that this equation, the graph of it, has a y-intercept at -7 and has a slope of 5, which we'll talk about that again later in the chapter. And so go up 5 over 1, and we get a line, pretty steep line, but it does something like that. Now the graph of this thing is useful in determining the domain and range because the points on this line, all the points in the line, represent ordered pairs in the set. And so if you think about all of the x values that give you points on the line, that's everything, right? This line extends indefinitely to the right and indefinitely to the left. And so every x value, no matter where it is, corresponds to some point on this line. You know, it extends indefinitely. So everything is on there, and so the domain is all real numbers. Same thing with the range, with the y values. This line goes up indefinitely, it goes down indefinitely, it has no gaps in it. And so every value on the y-axis has a corresponding point on the line. And for that reason, the range is all real numbers. Okay, so the range is the part of the y-axis that's covered by the graph. Okay. There are lots of equations that have domains and ranges that are not all real numbers, where there's things that are pulled out or don't work. Don't know that it shows up just yet. No, we don't see that yet. We'll see it in the next couple sections later in this chapter. Okay, so the other thing we'll work with in this section is something called function notation. And I'll go back to that previous example, 5x minus 7. It's kind of a nice one to work with. And so I had that table and I just erased it. Let's see. So one of the points on that table was 1 comma, if I plug into 1 is -2, right? That was one of the points on the table. Because when I plug in a 1, I get a -2 out. So, what was I going to say? Oh, so this represents an x value of 1 followed by a y value of -2. Those two things combined together give me a point on the graph and give me an ordered pair in the set. Now, a function is a very special type of relation. I didn't define function yet, so I got to do that. So a function has exactly one output, or I should say, how do I want to write that? Exactly one domain, no. Hold on, it's in my head, it's just not coming out. It has exactly one range value for each domain value. It has exactly one range value for each domain value. So it's a special type of relation. My computer's sleeping. Okay. Well, if my computer keeps falling asleep, I hope I'm not boring you guys to sleep as much as the computer's falling asleep. Okay. Okay, that was a joke. You guys aren't laughing. At least I can't hear you. Anyway, so function has exactly one range value for each domain value. There are certain types of relations. Okay, you are laughing. See, yeah, okay, I can read your laughter. That's good. That's terrible. Let's see. So, no, I lost my train of thought. Oh, there are certain types of relations where this is not the case, where you can have the same x value gives you multiple y values. Those are actually not I don't know, they're not as useful or as easy to work with as functions are. So functions require one range value for every domain value. An example, something like this, where you would have, if you think about having a single domain value like the number 5, and corresponding to it are multiple range values, like a point here at 5, 1, and then a point up here at like 5, 4. If you have multiple range values for the same domain value, this violates the definition of a function, so it's not a function. And really, that's going to happen anytime 2 points line up vertically. You'd have a fixed domain value with multiple range values. That's going to violate that definition, so those will not be functions. Oh, cricket's chirping. Thanks, Wakeman. Yes, that's probably what it was. Okay, so those are not functions. The result of this is that if you were to plot the graph of a relation and you find any 2 points that line up vertically, it's not going to be a function. But if you never have points that line up vertically, then you're going to have a function there. Okay, so we have this thing called the vertical line test. This is going to be pretty important, the vertical line test. It basically says that if at least one vertical line crosses the graph 2 or more times, the graph does not represent a function. So if at least one vertical line crosses the graph more than once, then the graph is not a function. Okay. So you cannot have a vertical line that crosses the graph more than once. If you do, it's not a function. Okay, so in this case here, the one I just wrote, if you sketch in a vertical line through those 2 points, it hits more than once. It's kind of a weird example because they're the only 2 points. But if I had another function or another graph, maybe something that did this, like a snaking or an S shape, you can see the y-axis itself hits the graph more than once. We've got point there, there, there. It doesn't have to be the y-axis. That's just the obvious one because it's already there. But because there's a vertical line, hits the graph more than once, it's not a function. Okay. But if every single vertical line that you could possibly draw hits the graph once, or not at all, maybe it misses the graph because there's no point there, that's okay. Then you have a function. Okay. Okay, so that's called the vertical line test. You just think about drawing vertical lines in, and as soon as the vertical line hits more than once, it's not a function. Okay, so when you have a function, it's very nice because every input gives you exactly one output. And the example I wrote up here is one of them, is an example of a function. Okay. What's nice about functions then is I can predict that whenever I plug a number in for x, I'm only going to get one thing out for y. There's not multiple options that I could get out. And that makes sense on this one because no matter what I plug in a number, if I multiply by 5, there's only one possible answer to that. And if I subtract 7 from that result, there's only one possible answer there. Right? So as an example, if I wanted to plug in an x value of 9, I know for a fact that 5 times 9 only has one answer. And I also know that that answer minus 7 will only have one answer. And so the final answer, well, there's only one possible outcome, right? So the y value must be, well, 45 minus 7 is 30, whatever, 38, right? 38. So 38 is the only possible answer. There isn't more. There's no more option than that. There are some equations where you can get more than one answer. Okay. Usually they involve like a plus or minus or some weird thing in there. But in this case, we're good with that. Okay. So this is definitely a function. There's only one possible output for every input. And for that reason, then, we can use a new notation called function notation. So function notation basically relates the input and the output in the same equation without having to write them separately. So let me show you an example, and this is the last thing we'll do. We'll get out of here after this. So I appreciate you guys following through and getting through this class period today. We're almost done. So function notation in this particular example, we're going to say that that y is a function of x. Okay, so y is a function of x. And so what I have then is this notation. We're going to say f parenthesis x parenthesis equals 5x minus 7. This notation, f parenthesis x parenthesis, is a notation that represents f of x, or function of x. We usually speak it or write it as f of x, meaning it's a function of x. And all that really means then is that x is the input. You plug in the x, and then the function, which is the equation, the function gives you out an output, some other number. You can almost think of it like a machine, right? Or a vending machine almost. You put money in, and you get out a pop, right? Or you get out a candy bar out of a vending machine. So you plug something in, you get something out. So a function is nice because you know that whatever you plug in will only give you a possible outcome, or one possible outcome. So it's not really like a vending machine, because in a vending machine, all the pops cost the same amount, right? So you plug in a certain amount, and you could have a variety of outputs. But imagine that each pop costs a different amount of money. You could just plug in the amount of money, and it would spit out the pop. It would know which one that you wanted based upon how much you plugged in. Okay, so it's a little bit different. I guess the analogy is not quite there. So let's see. In this example here, I had the point 1, negative 2. I can represent that in function notation by writing f of negative 1. Remember, negative 1 is the x value. It's the number you're plugging in. I'm sorry, not negative 1, positive 1. Positive 1. And then the negative 2 is what you get out. So f of 1 is equal to 5 times 1 minus 7. 5 minus 7, which is negative 2. Okay. And so the x value is what we typically call the input. It's the independent variable and the input. They both start with in. Okay. It's the number that you plug in to the function. The y tends to be the output. It's determined by the input, so it's the dependent variable. So input and output. Whatever, just as a note, computer's falling asleep again. Okay. Just as a note, then, whatever is in the parentheses is the input. Whatever is not in the parentheses is the output. Okay, so the input is in parentheses. I'm not going to spell it all out. Yeah, in parentheses, and the output is out of parentheses. Okay, it's not. It's the one that's not in parentheses. Okay. So I don't know if that makes sense or not, but that's where we're at with that. So, but we could do this with any number then, any combination. So if I did the 938 combination, I would say, you know, f of 9 equals 5 times 9 minus 7, which is 45 minus 7, which is 38. So again, the 9 represents your input. The 38 represents the output. So that's your x value, and this is your y value. All right, so that's our function notation, and we can really plug anything in. We can plug in even some variables. We don't have to just plug in numbers. So let me throw a different example up there real quick, and then maybe we'll call it a day here. So maybe we're not going to get out as early as I hope. So if I had, if f of x is equal to x squared minus 3x, okay, this one is a function. Let's say I wanted to find f of x plus 2, something like that. So in this case, I'm taking an expression, not just a number, but an expression, and plugging it into the function. And so each of the original x's gets replaced with what's in the parentheses. And so I have this x becomes x plus 2, and then I got to square that, and then I get a minus 3, and then this x becomes another x plus 2. So again, any of the original x's gets replaced with whatever I'm inputting, whatever's in the parentheses. And so it becomes a much more complicated expression. But of course, I could expand that out and make it look nicer, right? X plus 2 squared. Remember, if you square something, you multiply it by itself. And then here, the minus 3 could just distribute in. That's pretty simple. Minus 3x minus 6. Hopefully, you guys have seen the FOIL method before. When you multiply two factors together that each have 2 terms, you do the first, outer, inner, last. We'll talk more about that in chapter 4, but for right now, we'll see it a few times periodically before we get there. Or maybe it's chapter 5. It's one of those chapters. We'd have x squared plus 2x plus 2x plus 4. And then I still have my minus 3x and my minus 6. So this ends up, we can combine like terms. X squared is different from everything else. I've got 2x minus 3x. So it's 4 minus 3, which is 1x. And then the 4 minus 6 gives me a negative 2. All right, I know I ran through that kind of fast. So I'm just trying to get through this before the end of class here. But the concept, again, is just whatever is in the parentheses replaces all of the x's in the equation. Okay? So if this was just a number, like if I just plugged in, you wanted to plug in f of 5, for instance, then I would have, you know, 5 squared minus 3 times 5. It'd be a lot easier, right? If it was just a number in there, right? F of 5. So it just depends on what's being inputted into those parentheses, right? So you just plug it in for the x's, replace the x's with it, and then simplify.